Hello everyone! Great to see you all chose to attend this presentation in which I will present the work that I've done together with Fabian Jarmolowitz at Bosch and Riccardo Ferrari at the Delft Center for Systems and Control on cyber attack detection in collaborative intersection control. In normal traffic, intersections are a major cause of accidents and traffic delays, as this brilliant educational video so perfectly illustrates in just 10 seconds.
Did you notice how I came to a complete stop?
Very good. Now, who goes first?
And did you notice how she came to a full and complete stop? Well, exactly this inefficiency of intersection is why so much road planning effort is being put into new designs of innovative intersections to both increase throughput and safety. In this video, some novel intersection designs for increased throughput are showcased. However, these solutions are costly and often take more space than traditional intersections. And with the help of automation in the car, by means of autonomous control at the intersection, throughput at the intersection can be increased without needing this additional infrastructure. Specifically, with the help of emerging communication technologies and standards for vehicle-to-vehicle communication, so-called collaborative intersection control can be made possible. In collaborative intersection control, cars approaching an intersection use LiDAR to sense distance and relative velocity, and collaborate by communicating their intended acceleration over a vehicle-to-vehicle communication network. This communication can be used as a feed-forward term and greatly improves the intersection control performance, but also brings the risk of cyber attacks, either by a remote attacker or by a local agent that can infiltrate the communication system. One can easily imagine that the communication can be changed such that a crash occurs at the intersection. And therefore, to assure safety of any intersection control solution, any harmful attacks will need to be detected well before they can cause a crash, such that an appropriate control action can be taken. Now, in previous work, we have already developed such a detection method based on a sliding mode observer, but for collaborative vehicle platoons. Now, a collaborative vehicle platoon is the situation where cars follow each other autonomously using a LiDAR sensor to measure the distance and relative velocity and communicating the intended acceleration to increase performance, which however also brings with it the chance of cyber attacks. Therefore, to assure safety in any collaborative platooning solution, harmful attacks need to be detected before they can cause a crash. Now, if it sounds like I've been telling the same story twice, that's because I have. Because by projecting the collaborative intersection control scenario onto a straight road, exactly the collaborative platooning scenario is obtained. And therefore the existing detection method for collaborative platooning can directly be applied to intersection control. The existing detection method is implemented in the car that is receiving the communication, where local measurements as well as the received communication are used to feed a sliding mode observer, which will provide us with a state estimation, an output estimation error, which is the difference between the true output and the estimated output, and the switching feedback term that is used to obtain the state estimation. Now, by filtering this switching term, the unknown input, which in our case is the attack, can be estimated, and this estimate is then compared to a threshold to perform detection. This existing detection method from previous work is extended from a sliding mode observer based state and unknown input estimation method, which was first introduced in a highly cited paper by, among others, Christopher Edwards. Now, using this sliding mode observer, theoretically exact state and unknown input estimation can be achieved, under the assumption that the system contains only matched uncertainties and that the measurement has no noise. And once exact state estimation is achieved, also the unknown input, which in our case is the attack, can be exactly estimated based on the switching term. And because the estimation of the attack is exact, also attack detection in this case is trivial. However, if we use the same observer without these idealized assumptions, then this no longer holds. And therefore, in our previous work, we've designed a cyber attack detection threshold where attacks can be detected for systems with unmatched uncertainties and with measurement noise. And in order to do so, we have transformed the system to obtain a measured and an unmeasured part of the observer error, E1 and E2. And we found that the unmeasured part of the observer error, E1, converges to a bounded area around the matched uncertainties, and that the measured part of the observer error, E2, is confined to be smaller than the maximum value of the measurement noise. Also, we have defined bounds on the rate of change of the measured state observer error. Based on these bounds, we have found that the attack can be estimated with bounded uncertainties, and that we can detect an attack if it becomes larger than a defined threshold. And by applying this method to an intersection control scenario in simulation, we obtain the following results. We compare the attack estimate in blue with the threshold in purple, and we see that the estimate exceeds the threshold around 3 seconds, meaning we have a detection at around 3 seconds, leaving only about 2 seconds for determining and implementing an appropriate control action. And this short time to do so will mean that it will probably be quite a harsh control action to still avoid detection. And therefore in this work, we strive for a faster detection, such that more time is available for a control action. Looking at the attack estimate-based detection, one cause of delay can readily be identified. In order to obtain the attack estimate from the switching term, it is filtered, which introduces a delay. And therefore, the novel detection approach will directly use the observer error dynamics to detect the attack. We will use the output estimation error EY together with the model knowledge of the healthy system to generate an overall bound on E2, the state estimation error. And then these bounds are compared to each other in order to detect the attack. Now to generate these bounds, we will use all the known bounds on the error dynamics to create a combined bound on E2. So first we take the two bounds that we have already identified earlier, and these bounds will signify the modeled healthy dynamics. They only depend on the model. Now note that E2 is the state estimation error and it's not directly known. But what we do know is the output estimation error, which is separated from E2 by the measurement noise. And based on this EY, this output estimation error, two more bounds can be added which signify the real attacked dynamics. Because if the system is attacked, then EY will change due to it. And the first bound we can introduce is that the difference between EY and E2 is at most the maximum value of the noise. And secondly, we can say that the sign of the rate of change of E2, the state estimation error, is negative the sign of the output estimation error. And based on these four bounds, we will design one combined bound of the state estimation error. We start when we have a measurement. Then we get a new value for EY. And based on the two bounds that are indicated now, we can also take an area in which E2 will be located based on this measurement EY. And based on the bounds on the rate of change of the state estimation error, we can propagate this bound unto the next time when we get a measurement. And then, of course, we get a new measurement and we get new bounds for E2. And the final combined bound can now be obtained by taking the intersection of these two bounds, the propagated bound and the new measurement-based bound. And then we can do this at every time step, and this leads to a time varying bound on E2, which is valid for all time. And in healthy condition, then the following condition should always hold. E2 is always between the lower bound and the upper bound on E2. But as we already mentioned before, we don't know E2, the state estimation error. We only know EY, the output estimation error. And therefore we cannot directly check this condition. But the condition that we can check is the following. And this condition implies, a violation of this condition implies violation of the previous condition, and therefore it also warrants an attack detection. And using this detection criterion, the following theorem has been presented. There exists a tau and delta such that detection occurs within tau seconds if some function r of the attack is bigger than delta during this time tau. And here tau and delta can be expressed analytically in terms of the model and observer parameters. Now in simpler terms, this means that if the attack is sufficiently large and persists for sufficiently long, and we know exactly how large and long this has to be, then the attack is guaranteed to be detected. Now using the same simulation scenario as before, the new detection method gives us the following result. And one can see that the detection happens much faster here, already before 1 second, leaving almost 4 seconds for applying the appropriate control action, compared to only 2 seconds that were available using the old attack estimate based method of detection. Which means that this method performs much better. And furthermore, as both methods stem from the same observer, the existing attack estimate from the old method can still be calculated and used together with the new faster detection method. So in conclusion, we have designed a novel sliding mode observer based detection method directly using the observer error dynamics. By doing so, we circumvent the delay that is introduced when obtaining the attack estimate. And this causes the novel detection method to be faster, allowing for more time for implementation of some appropriate control action. Furthermore, this method can be easily used concurrently with the existing attack estimation capabilities of the sliding mode observer in order to take the best of both worlds, fast detection and exact estimation. In future work, it would be interesting to see how the novel attack detection method and the existing attack estimation capabilities can be combined to form an integrated cyber attack tolerant control law, bringing us even closer to truly safe collaborative intersection control. Thank you for your attention, and I will now answer any questions you might have.